4, and we will be discussing probability. And so the basic outline, as you see here, initially we're going to be going over some of the basic concepts of probability, and then we'll be going on into the how to add and multiply different probabilities. What's the implication there? And then we'll go on to these other guys here. 4.3 will be kind of skinny if we go over it at all, and then these guys will come on later. Okay. So a quick overview. We're going to be discussing what is probability, what is an event, and a simple event, a sample space, complement, and then 3 common approaches to finding the probability. And then lastly, we'll talk about actual odds versus payoff odds. Okay. So we want to learn how to interpret probability values. Probabilities are commonly expressed as a value between 0 and 1. And if you had an event, we'll call an event X. An event X. The probability of this event X, and we'll talk a little bit later about what we mean about probability or an event means. This will always be between 1 and 0. And so small probabilities correspond to rare events. If I said something has a probability of 0, or a particular event had a probability of 0 of occurring, what would that mean? What do you guys think that would mean? It's just not gonna happen. So you have all the way from here, not, I'll use the colloquialism gonna, not gonna happen. What about if the probability has a value of 1? That would mean it is as certain as the sun is going to rise tomorrow. So 0 means it will never happen. 1 means it is inevitable. It will happen. So next we're going over odds and how they relate to probabilities. Odds basically are a ratio of the probability of an event versus a probability of an event not occurring. Usually they're expressed as a ratio of 2 whole numbers. And so okay, so basics of probability. Here we're going to get down some vocabulary. Again, unfortunately, in this class, there is a lot of vocabulary to learn. This simply helps us speedily transmit what we're trying to communicate if we all know what the vocabulary means. So an event. An event is any collection of results or outcomes of a procedure. So you have a procedure, an experiment that you're looking at, and the event is simply the results of that procedure. Now a simple event is an outcome or event that cannot be further broken down into simpler components. For instance, flipping a coin is either going to be heads or tails. It cannot be broken any simpler. Or if you're looking at a coin being flipped twice, a simple event would be heads and then tails. Right? In this case, the order counts. Tails and then heads would be another event. Okay. And so the sample space is the collection. It's a collection of all the possible events. You typically would write them out in brackets, right? You'd have a bracket here, and then you'd start listing off all your events, separated by comma, and then you would close your bracket. And that is, of course, assuming that you have a series of discrete events that you are trying to analyze. Okay. All right, so let's look at some examples. So we're looking at the simple events and sample spaces. In this guy, we've got the following. We're going to use B to designate boy. Let me change colors here. B to represent boy. And we're going to use G to designate girl. And we're talking about births. You know, if you give birth to a boy, that would be the event B. And if you give birth to a girl, that would be the event G. Okay. So procedure 1, single birth. So a simple event might be one girl, or the other event would be one. Thank you. So it's either one girl or one boy. And so the list, our sample space, all the events we would list, we would have right here. It's either a boy or a girl, and that's all we have listed here. Okay. What about for 3 births? Here it gets a little bit more involved. Time's up. It's a little more complicated because we have more events that could possibly happen. And so you could have a boy, or you could have a girl first, and then after that you could have another boy or another girl, and then going on up the list, another boy, and then another girl. And so this would be the sample space: boy, boy, boy. Okay, and which we have listed right here. And then it could be boy, girl, boy, girl. Okay, so and then here's this one, which is boy, boy, girl. And then we have boy, girl, boy. Okay, and I can keep going with this, but I think you guys are getting the idea. Where basically you can kind of create this map, this tree, and as you go further out, you get all the events listed in this way. All right, any questions? Okay, so with one birth, the result of one girl is a simple event, as we discussed. And the result of one boy is another simple event. And they are individual simple events because they cannot be broken down any further. So again, the emphasis here that we're trying to make is a simple event is one and only one unique way that the event can happen. So let's look at some more simple events. With 3 births, the results of 2 girls followed by a boy is a simple event. That was one of the ones that we looked at. Well, we didn't map it out, but it was one of the ones we would have gotten to. However, if I said, what about the event 2 girls? Well, those have a couple of different possibilities. This is one, 2 girls, 1 boy, or it could be a boy and then a girl. There could be a girl, boy, girl. And so the event, the space, the sample space where we have 2 girls is not simple because there are multiple events that give that particular outcome. Okay. So how about rolling a single dice? The outcome of 5 is a simple event, but the outcome of an even number is not a simple event. Right? So, for instance, for 5, it's just that's 1, and for it to be even, this there could be 2, 4, or 6. How do they do 6? 1, 2. Like that, okay. Thank you. So yeah, so this would be the event of 5, and this is the event of an even number. Okay. All right, any questions so far? Okay, so not a simple event. With 3 bursts, the event of 2 girls and 1 boy is not a simple event, which is what we just went over, because it can occur with 3 different sample events right there. All right. And so again, sample space with 3 bursts. The sample space consists of the 8 different simple events listed in the above table or below table here. And you can come up with this table, you can come up with this table systematically by doing that little tree of all the events that we showed about, I guess it would have been 5 slides earlier. All right. All right, let's do this discussion example. Just going to spend a few minutes. So we have a sample space of the first 3 flips of a coin. What would that sample space look like? So kind of start drawing that out on your own sheet of paper. I'll give you probably about half a minute to look over this one, and then pause, and we'll take a look at this one right after that. Yeah, no, that was a sample space of, because I know exactly what this one's supposed to be, of the first 2 pitches in a baseball. We'll do that one for the second one. All right, so when you map this guy out, since I already have red on here, I'm going to switch to blue is used, let's go with green. What are the first 2 possibilities? It could be a heads or tails. And then the next one. And then, right. And so if we go along this branch right here, we get, that was an erase, not a highlighter, was it? Okay. We'll do it again. Heads, tails, heads, tails, heads, tails. So right here, if we go along this branch right along here, we would have what event? Right. Heads, heads, heads. What's the next event in this branch? Yeah, heads, heads, tails. Right, and then you can keep going. Oops. What color are we doing? Green, okay. And here we've got, again, heads or tails. And so we got heads, tails, no, heads, tails, heads right there. Heads, tails, tails. So you can see we've got a nice systematic way of getting everything on here. And so that's one whole branch. Then over here, well, we can branch it out again, but we realize it's just going to be repeated just with tails in the front. And so over here it just becomes tails, heads, heads, tails, heads, tails, 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 heads, and then tails, tails, tails. So if we wanted to list off all our events, we would, our sample space, we would just write them all out. Heads, 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 tails, heads, tails, heads, and so on until you got everything written down in between those brackets, and that would be our sample space of all the events. Okay, and once again, we change this so as not a repeat question, but we want to know what are the possible outcomes of the first two pitches in a baseball game. So first off, what are all the possible outcomes for a single pitch? Yeah, there could be a strike. What else could there be? Could be a ball. What else? Could be a foul. Let's just summarize, like if it's a foul or if it goes out there as just an H, and that'll encompass both of those. Basically, he hits the ball. He makes contact. I know there's a couple of different events we could spiral off of that, but we want to keep this example simple. All right. Are there any other outcomes? You could get beamed. And so let's see. We're already using the B. So what we use for beam? What's that? Yeah. Well, we're putting that under our H. Like where he hits, either gets, you know what, we'll just count. Basically the result is you get on base or you get all the way around, so we'll just put that in there with this guy here. So H is any event where he gets off of home plate and he gets the first, second, third, or home plate. And so that'll just be the simple event where he leaves home. All right, so first one. It could be a strike, there could be a ball, or there could be a hit. Okay? And then after that, what other events could happen? Yeah, strike two. Could be ball two, or no, first one strike, one ball, or he could get on base. And then you just repeat that for each one. You could have a ball, then a strike, ball two, or he could get on base. Then you have a strike, a ball, or there could be a hit. And so to construct our sample space, we would just list off each event. There could be a strike, a strike ball, strike hit, ball strike, ball, ball hit, hit strike, hit ball, or there could be a, well, there can't be a hit, can there? So note that whenever he hits it, that automatically kills that branch right there. Because it's a baseball game. Now, if you get on base, is there another pitch for that batter? No. So we would end it right there. So this would be our list of simple events that could happen for the first two pitches of the game. So based off of this, is the event that you get, that the batter gets one strike, one ball, is that a simple event? Does that happen more than once? Right, so since it happens more than once, does that fit our definition of a simple event? Yeah, no, so that would not be a simple event. What about two strikes? Is that a simple event? Yeah. So anything that only happens once in our sample space is considered a simple event. Okay. So identify the sample space, an event, and a simple event in each of the following. Basically the same thing we just did. You toss a coin once, that's either heads or tails. Let me probably don't need to go that quick. If you roll a dice once, that would be 1, 2, 3, 4, 5, or 6. And if you toss 2 coins, again, we've already been through that one. You just do your mapping. Heads or tails, heads, tails, heads or tails. Okay, any questions so far? Okay, and so here, when you're going back to the slides, this just goes over what we just talked about. Sample space here is heads or tails. Sample space here is 1, 2, 3, 4, 5, or 6. Again, that's for rolling a die, for tossing a coin. And then for tossing 2 coins, you have these different events here. Okay. All right, so once again, P denotes a probability, and A, B, and C typically denote specific events. And so if we write P of A, that denotes the probability of A occurring. All right. And once again, here's a visual representation of what I was talking about earlier on. You have something that is down here. It is unlikely. Usually we define this as 0.05. It's important to note that is not rigid, but that's typically what we would say is falls under the heading of unlikely if it is in this zone. And then for something that's likely, we would typically put a 95% chance by convention. And once again, these are not rigid rules. These are just more rules of thumb that we tend to go by. Okay. So the common approach is defining the probability of an event. Simply take the number of times A occurs and divide it by the number of trials it was repeated. This assumes that each event is equally likely to occur. And so if we were to use this method, or this method, let's go over this before I get to jump to this. The other way is simply take the number of ways A can occur and divide it by the number of simple events in the sample space. So let's think about the example where we talked about the pitcher throwing a strike, the probability of him throwing a strike. We could say, if we use this method, versus this method, which one do you think would more accurately represent what was going on? The number of ways it can occur, or you simply look at the number of times he threw a strike versus the number of times he pitched? Which one would you pick? You would want to look at what actually happened, right? That would be the better way. You wouldn't just look, okay, he could throw a strike, he could throw a ball, or he could hit him. If you do it that way, he has a 1 in 3 chance of getting a strike. But that doesn't take into account the pitcher's skill or the batter's skill. Or maybe the particular stadium he's at gives some advantage to the batter or to the pitcher. And so in that type of situation, you'd want to look at the number of times A occurred. What about flipping a coin? It's just a 50-50 chance. And so you would, in that case, you would just look at the number of ways it can occur, which is only 1, versus the number of possible outcomes, which is 2. 1 divided by 2, 50-50 chance. And this method is called the relative frequency approximation. It's also known as the empirical method. Okay. And once again, this is, you construct an experiment with a large number of times and count the number of times the event A actually occurs. And this down here is called the classical approach of calculating probabilities. And again, if you have indifferent results and S number of ways the particular event can occur is simply S divided by N. This is your probability game, such as flipping a coin, rolling a dice, or what have you. So we've talked about two. There's a third way, and this is called the subjective probabilities. Basically, this can be summed up with you have a hunch. You know, you notice something seems to occur a certain number of times, so you simply just assign a probability. Usually this method is anecdotal, and I would caution against using that as a legitimate way to calculate the probabilities, but in many times it offers a very good first step towards figuring out the real probabilities. Okay. So simulations. Sometimes none of the preceding three approaches can be used, and in this case you might want to create a simulation of a procedure. And a simulation is basically some process that behaves in the same ways as the procedure itself so that similar results are produced. So sometimes you might have complicated, like a lot of different factors feeding into one particular event, each with their own probabilities, and so you might just say, okay, we roll the dice for this event happening and roll the dice for this event and see what happens, and you keep running through it until you and see what comes out, and that would be your simulated probability. And that would be something from real life that you can do. Also, a lot of times people use the same method, but they'll simply do this with a computer simulation. You'll hear the term Monte Carlo type simulation sometimes out in the field, and that's exactly what this is. It's just a simulation of an event where actually knowing the probability is problematic, so you create a simulation to figure out what's going on. Okay. Okay. Rounding probabilities. Basically 3 decimal places is what you'd want to use. With the quick suggestion, if a probability cannot be done as a simple fraction, such as 2/5 or 5/9, because those are pretty easy to wrap your head around. If it's not a simple fraction that's easy to understand, that's when you'd want to use this decimal approximation, and once again you would use 3 digits. Okay. All right. You got it? Okay. Law of large numbers. So, as a procedure is repeated again and again, the relative frequency probability of it tends to approach the actual probability. So, for instance, if you flipped a coin, and we'll run an experiment here in just a second, if you were to flip a coin and you got heads 3 times, is it fair to assume that, well, we got heads 3 times in a row, surely that's 100% probability that the next one's going to be heads? No, that's not correct. And so the next one does not affect the other one, but as you keep flipping the coin, you'll begin to approach the true probability, because each one has its own chance of happening one way or the other. Okay. All right, so once again, the law of large numbers. A few cautions. The law of large numbers applies to behavior over a large number of trials. And as we saw in the demonstration we just saw, we ran through 439 trials of a virtual flipped coin, and we got to 50%. And it wasn't until later on, not the first 10, 20 flips, but even at 100, it was still some distance away from 50-50. And note that it does not apply to any one individual outcome. In one of the simulations we ran, we got tails 3 times in a row. And the fact that we got tails 3 times in a row had no bearing on whether we would get tails the 4th time. Okay. And then one more word of caution. If we know nothing about the likelihood of different possible outcomes, we cannot assume that they are all equally likely. So when we ran the simulation, we assumed that we were dealing with a fair coin. If we knew that the coin was not fairly distributed ahead of time, we might have been able to apply that to our simulation as well. But in this case, we assumed a standard US coin, which in fact I believe is for the most part really well balanced. Okay. And do not forget that actual probabilities depend on factors such as the amount of preparation and test difficulty. So in our flipped coin example, we also assumed when we did our virtual experiment that I did not have some special flipping technique that I would employ to get heads more often than tails. All right. So let's look at this one. We're dealing with the probability of dying when skydiving. Any skydivers out there? At least one. So in a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in death. We use the relative frequency approach as follows. Number of skydiving deaths divided by the number of skydiving jumps. And so when you look at the 21, you can say, wow, skydiving is kind of dangerous, but when we calculate the probability, we see it's in fact a very low probability. It's less than 1% chance, much less than 1% chance. And so, and here you always have to assume the classical approach cannot be used because the two outcomes, dying or surviving. Real fast, does anyone remember what is the classical approach? The classical approach is when you take the number of outcomes divided by the single outcome. So if we took the classical approach, you would either live or you'd die. Those are the two outcomes, and that would be our sample space. And so if you want to calculate use the classical approach to determine what your chances of living or dying, you would go, okay, there's two outcomes, and so the probability of dying is 1 out of 2, which is 0.5, which does not accurately predict what actually happens. Okay. Okay, texting and driving. I know no one here texts and drives at any point in time, and I know this is something that I have never been guilty of in my entire life. I hope it's obvious I'm being a little bit sarcastic there. So over this study of the U.S. high school drivers, and this was over a period of 30 days, 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving. If a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. So how would we calculate that probability? We're not going to run through the numbers, just how would we calculate that? So we just pull a random high schooler, and we want to know, did they text or not during the past 30 days? What's the probability? We'll say probability T, where T stands for texted. And anytime you use a symbol like this, whenever you're doing your work, you always want to define your variable so that when someone else comes by to look at your work, they'll know what you're talking about. And more importantly, if you come back to your own work a week later, you know what you're talking about. Memories are not perfect. I'm sure you've noticed. So for this, we'd say T means texted while driving. Okay. So don't think about the numbers. How would we calculate this? You would take the, based off the
times people texted while driving.
Yeah. Yeah, the number of those who texted. Okay, let me squeeze an E in there. There we go. Those who texted divided by the number and study. And in this case, that symbol is a pound sign meaning number. It is not a hashtag. That's what it meant before this. Okay, so first we have to figure out what was the total number in the study. So we're showing you guys how to break it down into parts. You don't always have to do all the calculations in one step. As a matter of fact, oftentimes it's preferable to break your calculations up into chewable chunks. And so here we just add everything up and we get the total being 8,505. All right. And so after this, we use the relative frequency approach, not the classical approach, as follows. The probability of texting while driving, which again we use the letter T. Drivers who texted while driving divided by the number of drivers in the sample. And when you run that calculation, you find that the probability of finding a random high schooler texted while driving in the past 30 days was about 44.5%, or 0.445. Okay. Any questions? Okay. And that's just the interpretation of that number, which is exactly what I just said. 0.445 probability that if a high school driver is randomly selected, he or she texted. And again, that is a 44.5% chance. Okay, oops, sorry. All right, any questions on that example? Now, what if we use the classical approach? What would the probability have been? 50-50. And we see here there is a not insignificant difference between a 50-50 and what we actually calculated. Okay, the complement. This is not something you tell someone when you're trying to make them feel better. This basically means everything except what you're looking at. And so if you think of this in terms of pictures, say A is, say we got a big circle here and everything, and A is over here. That's our event. A would be everything not a part of the event. And here we're using A bar, but also I've seen AC to stand for A complement, and oftentimes you'll see A prime. These are very commonly used symbols for the complement, although in the book I believe they'll be using the bar notation. Okay. Okay. Returning to the skydiving example. Again, we had 21 of them resulting in death. We want to find the probability of not dying when making a skydiving jump. So it was 0.45, if I recall correctly, was the probability of dying. But to find the probability of the complement, and I'll match the book's bar notation, although it's not my favorite notation for this kind. if the sum of all the probabilities has to equal 1, and A is the probability of one event and A is everything else, what must the sum of these two probabilities be? If the sum of all probabilities is 1, just 1. Okay. All right, so among the 3 million jumps, again, there were 21 deaths, and I believe that was, again, was 0.00 something percent. What did we calculate? It was 0.000, well, we can look at it right here. 0.000007% was your chance of dying. So the probability of not dying, i.e. the probability of living, is 0.99993. That was a pretty good probability. So would you conclude from this that skydiving is safe? How about scary? You be scary. Still be safe, but be scary. All right. Review. The probability of an event is a fraction or decimal. We can sometimes report it in terms of a percent, but when we're thinking about probabilities, we typically want to do our calculations in the decimal format. And when you put it in the decimal format, it is always going to be between 0 and 1. And this inclusive means you can include the 0 or you can include the 1. So the probability of any given event looks like this. All right. And again, the probability of an impossible event is 0. So if the probability of an impossible event is 0. Okay. So then the probability of an event that is certain to occur is 1. And again, here's the notation. P of A means the probability of an event A. P of A prime is the probability of an event A not occurring. And as we talked about before, some of the other notation is A prime or A complement. And of course, the sum of all the probabilities equals 1. Okay, so rare events. And again, if you refer back to the earlier on in the lecture, we talked about 5% chance being our threshold for an unlikely event. But again, that is not a rigid number to go by, but is a loose rule of thumb. If we assume the probability of a particular observed event is very small, and then we find that the observed event occurs significantly greater than what the assumption predicts, well, then you have to update your assumption. We can conclude that the assumption is probably not correct. And I realize this is probably kind of a duh statement, but this does come into play as we will go through the slides in the next sections. And we'll be exploring it in greater detail. So we want to make sure we're all on the same page here. Okay. Using probabilities to determine when results are significantly high or significantly low. So if we have significantly high number of successes, with X successes among N trials is a significantly high number of successes if the probability of X or more successes is unlikely with a probability of 0.05 or less. I know that's a bit of a mouthful, but what we're saying here is that we're using this number here to define whether or not something is likely to happen or unlikely to happen. Okay. And then on this one, it's just the same concept, but again, now we're instead of dealing with high numbers, then we're dealing with low numbers. And so basically we're on the 5% on either end. So basically this is 0 to 1. And so this is 0.05, 0.05. Like so. Okay. Okay, and now we're at odds, which is where I wanted us to end up at. So we will be closing it right here. If you have homework questions, I will stick around. If you do not wish